Welcome to the debate. Today, we are staring into the abyss, quite literally. For decades, the story of our universe seemed to have this clear, almost comforting architectural blueprint. It was a story of gradualism. We believe that stars formed first, lived their lives, died in supernovae, and then left behind these small black holes. And over billions of years, these small stellar remnants would merge and eat and just claw their way up to supermassive status. It was a hierarchical climb from the bottom up. But the James Webb Space Telescope, JWST, it's effectively taken a sledgehammer to that timeline. We're now seeing supermassive black holes, monsters with millions, even billions, of solar masses existing just 400 to 500 million years after the Big Bang. They are, to put it bluntly, too big and too early.
And that is exactly where the excitement is. I mean, it's not just a minor adjustment of the timeline. I would argue it's a fundamental crisis in cosmology. These observations suggest that the infant universe was already gravitationally mature in a way our standard models just strictly forbid. So we're looking at a scenario where the universe was kind of littered with giants from the very start. The comfortable story is dead, and now we're scrambling to read the new one.
Right. But the question, though, is whether this requires us to throw out the physics we know or just to apply it more creatively. I am the advocate, and today I will argue that while the data is surprising, we can explain these early giants through modifications to our standard understanding of accretion, basically beating frenzies, without inventing entirely new physics or these exotic seed mechanisms.
And I am the dissenter. And my position is that the standard model is effectively broken. The hierarchical growth of black holes from stellar remnants, it just cannot mathematically account for what JWST is showing us. We are witnessing a real revolution that points toward heavy seeds, black holes that were, born big, formed by direct collapse, or perhaps even from primordial origins that predate the stars themselves.
Okay, so let's get right into the heart of the problem. We are talking about redshifts greater than 10. Now, for those in the audience maybe not glued to their spectrographs, redshift is essentially our measure of distance and time. The higher the number, the further back we're looking. At redshift 10, the universe is less than 1 billion years old. Under the standard hierarchical model, which has been the cornerstone of astrophysics, supermassive black holes start as light seeds, the remnants of population 3 stars, maybe 10 to 100 solar masses. To get from 100 solar masses to 1 billion, that requires time, a lot of time.
Exactly, and time is the one luxury these objects do not have. You're trying to run a marathon in a sprint. The math just doesn't close.
Okay, I'll concede the timeline is tight, but I'm just not convinced it's impossible. Before we declare the model broken, we have to look at the feeding mechanism. The standard limit, the Eddington limit, regulates how fast a black hole can grow. To put it simply, if a black hole eats too fast, the friction creates this immense heat and radiation. That radiation then pushes outward against the infalling gas. It's like trying to drink from a fire hose that's pushing you backward.
Right.
Eventually, the black hole chokes on its own meal and growth stops. This limit is why the hierarchical model takes billions of years. But we know limits can be broken.
Limits can be broken, sure, but not consistently for 400 million years straight.
Well, let me finish that thought, because the mechanism here really matters. I'm looking at the recent simulations by Daxel Metha at Maynooth University, published just this month in Nature Astronomy. They show that in the early universe, which was chaotic and incredibly gas-rich, light seeds could engage in what's called super-Eddington accretion. The simulations show that if the gas inflow is messy enough, turbulent, cold streams crashing in, the radiation gets trapped or it gets channeled out through the poles, allowing the black hole to guzzle gas at rates we usually consider impossible. Essentially, a cosmic feeding frenzy.
I've seen the Metha simulations, and they are impressive pieces of computation. I mean, they are. But let's be real about what you're suggesting. You're trying to patch a hole that is just too large. You're suggesting that these seeds grew tens of thousands of times their mass in a few 100 million years by consistently violating the Eddington limit. That requires a sustained feeding frenzy without any interruption. But turbulence goes both ways. It feeds, but it also disrupts. To bank on every single one of these giants having a perfect run of super-Eddington growth, it just feels like we are forcing the data to fit a model that wants to retire.
It is a conservative approach, certainly. It attempts to preserve the stellar origin story, which is based on physics we understand well. Stars die, they make black holes. Why is rapid growth less scientifically palatable to you than instant birth?
Because instant birth, or the heavy seed model, fits the most extreme anomalies we're seeing without requiring the black hole to break the laws of physics every single day for 400 million years. It's not just about the speed of growth, it's about the ratio of mass. If you start with a light seed, it grows alongside its galaxy. But we are seeing objects where the black hole dominates the entire system from day one. I'm talking about direct collapse. We're looking at massive gas clouds that skip the star phase entirely and collapse monolithically into black holes of 10,000 to 1,000,000 solar masses. That isn't a feeding frenzy, that is a distinct genesis event.
You're alluding to UAZ1, aren't you? That seems to be the poster child for your side of the table right now.
It absolutely is the smoking gun. Let's just look at the facts. Galaxy UHZ1, detected at a redshift of about 10.1, that's 470 million years after the Big Bang. We see it in X-rays with Chandra and in infrared with JWST. The black hole is estimated at 40 million solar masses. Now here is the kicker. That mass is effectively equal to the mass of all the stars in that galaxy. It's a 1-to-1 ratio.
It is a staggering ratio, I admit. In the Milky Way, for comparison, our central black hole is maybe 0.1% of the stellar mass. We usually expect the galaxy to be the iceberg and the black hole to be the penguin standing on top. UHZ1 is definitely what we'd call an outsized black hole galaxy.
Outsized is a polite way of putting it. It defies the hierarchical model completely. If that black hole started as a 100 solar mass seed, there is no physical way it catches up to the stellar mass of the galaxy that quickly, even with your super-Eddington feeding frenzies. The stars should vastly outweigh the black hole if they formed first. The fact that they're equal suggests the black hole was the primary anchor. It fits the specific prediction of direct collapse. A heavy seed forms first, and the galaxy struggles to assemble around it.
That's a compelling argument for UHZ1, and I acknowledge that specific object is a thorn in the side of the light seed model. However, UHZ1 is one data point. My concern with the heavy seed or direct collapse theory is that it requires incredibly fine-tuned conditions. I mean, to get a gas cloud to collapse directly into a black hole without fragmenting into stars, you need to keep it hot. That sounds counterintuitive, but if gas cools, it clumps into stars. You need a pristine atomic cooling halo. You need intense Lyman-Warner radiation from a neighbor to shut down star formation.
And maybe just explain Lyman-Warner radiation for a moment, because this is really key to the critique.
Right. So Lyman-Warner photons are a specific type of ultraviolet light that can destroy molecular hydrogen. And molecular hydrogen is the coolant of the early universe. It helps gas clouds shed, heat, and collapse into stars. So if you blast a cloud with Lyman-Warner radiation, you destroy the coolant. The cloud stays hot, it stays gaseous, and it doesn't shatter into a billion stars. Instead, gravity eventually crushes the whole massive cloud into a single point, a direct collapse black hole. But this requires a very specific setup, a nearby galaxy blasting this radiation at just the right time. It's a very specific recipe. Are we ready to say this happened everywhere? Or is UHC1 just a freak occurrence, a rare OBG that shouldn't be used to rewrite the history of the entire cosmos?
Well, it might be rare, or it might just be the first one we've caught because it's so extreme. But it's not just UHZ1. We have to talk about the little red dots. When JWST first turned on, we saw these things everywhere at redshifts of 6 to 9.
Ah, yes, the universe breakers.
Exactly. And why were they called that? Because initially everyone tried to interpret them as galaxies. And to make the light profile fit a galaxy, you ended up with something impossibly dense. Billions of stars packed into a region just 40 light years across. It physically didn't make sense. It would be like packing the entire population of Earth into a single elevator.
But that interpretation has shifted, hasn't it? The consensus is moving away from them being dense galaxies.
Right. And that shift supports my position. We now realize these aren't galaxies in the traditional sense. They are hidden engines.
Spectroscopic analysis shows these broad emission lines. For the listeners, when we look at the light spectrum, broad lines mean the gas emitting that light is swirling at thousands of kilometers per second. That's not stars, that's an accretion disk. These little red dots are point sources, less than a third of a light year wide, pumping out the energy of 250 billion suns. They are young, supermassive black holes, shrouded in dust.
I agree with the reclassification, but I interpret the implication differently. If we accept they're black holes and not stellar populations, the mass estimates actually drop significantly. If that light is coming from an accretion disk rather than stars, the black hole mass is likely 100 times less than the initial stellar mass estimates. That brings them down into the range of maybe 100,000 to 10 million solar masses. To me, that brings them back into the realm of possibility for the standard model, provided we allow for that super-Eddington growth I mentioned earlier. They are less universe-breaking and more universe-bending.
Bending is generous. Even at 10 million solar masses, you are pushing the absolute limits of what a light seed can achieve by redshift 7 or 8. But there's something else hidden in that data: the colors. This red isn't just redshift, it's a disguise. It's a dense, ionized cocoon. And this points to a transitional phase that the standard model doesn't really account for: the quasi-star or black hole star.
This is where we get into the truly exotic territory. Are you suggesting these objects are the hypothetical stars powered by accretion rather than fusion?
Precisely. Look at the object nicknamed the Cliff. That's Ruby's UDS 154183. It shows this incredibly sharp Balmer break in its spectrum.
Okay, let's pause on Balmer break.
Sure, a Balmer break is usually a signature of older stellar populations. It happens when hydrogen atoms cool down. But in this object, the break is sharp, yet the luminosity is off the charts. It's a contradiction. The leading theory now is that this isn't a cluster of stars, and it's not a naked black hole. It is a supermassive black hole buried inside a giant hydrogen envelope. The black hole eats the envelope from the inside out, generating heat that keeps the gas puffed up. It's a black hole star. This is exactly what a direct collapse object would look like in its adolescence. It's a monster wearing a star like a suit.
I do find the spectral evidence for the cliff to be very interesting. A Balmer break of that magnitude is certainly distinct. But again, is this a seed mechanism or is it just a phase of growth? You could argue that a light seed fed rapidly enough could develop a similar shroud. It doesn't necessarily prove the black hole was born at 10,000 solar masses. It just proves it's eating messing.
But look at the environment, or rather, the lack of one. Take QS01, discovered in 2023. We have a black hole of 50 million solar masses, and despite our best efforts, we cannot find a host galaxy. The researchers explicitly stated, and I'm quoting here, there doesn't really seem to be one. If you have a 50 million solar mass object with no visible stellar population around it, how can you argue that it grew hierarchically from a star cluster? Where are the stars? This supports the idea that the black hole formed first, in isolation, via direct collapse of a gas cloud. It was born big and alone.
Alone might be an overstatement. It could be that the host galaxy is simply faint or obscured, or that the black hole is so incredibly luminous it's just washing out the starlight. We see that dazzle effect in quasars all the time. However, I will admit that the lack of a detectable host for QS01 is, well, it's unsettling for the hierarchical model. It challenges the coevolution theory, where the galaxy and black hole grow in lockstep.
Unsettling is the word, and if we want to get really unsettled, we have to look even further back. We've been debating 400 million years post-Big Bang, but what about the first few minutes?
Primordial black holes. I knew we would get here.
We have to. You mentioned earlier that direct collapse needs fine-tuning, that Lyman-Werner radiation to stop star formation. You called it a specific recipe, but what if the seeds were already there? Stephen Hawking proposed primordial black holes formed from density fluctuations seconds after the Big Bang, but there's a new, more nuanced version of this. Not quite primordial black holes.
This is Windsor Chin's work out of NYU, correct?
Right. The idea tackles that fine-tuning problem. Around redshift 200, so just a few million years after the Big Bang, the cosmic microwave background, the CMB, was still incredibly hot. Hot enough that it naturally suppressed molecular hydrogen cooling. You didn't need a nearby galaxy blasting radiation. The universe itself was the radiation source. This would stop stars from forming and force those gas clouds to collapse directly into black holes. If this is true, direct collapse wasn't a rare fluke like UHZ1. It could have been the default mode of the universe before the first star ever ignited.
It is a theoretically elegant solution, I'll give you that. It removes the fine-tuning problem of the heavy seed model, and it would explain why we see so many of them. But the burden of proof is high. We would need to see a distinct lack of heavy elements, metals, and these objects to confirm they formed before the first stars polluted the universe.
And we are seeing that. Many of these high redshift targets have extremely low metallicity. They're pristine. That is the fingerprint of a pre-stellar origin.
Low metallicity, yes. Zero metallicity, we aren't quite there yet. But let's pivot to the consequences of these objects. Whether they started as light seeds in a feeding frenzy or heavy seeds born from gas clouds, they are seemingly everywhere. And they aren't just sitting there. They are active participants in their galactic ecosystems. In fact, they seem to be hostile participants.
The cosmic assassin theory.
Exactly. I'm thinking of Pablo's galaxy, GS10578. This is a massive galaxy, 200 billion solar masses, sitting there about 2 billion years after the Big Bang, and it is dead. No new stars are forming. And why? Because the black hole at its center is ejecting gas at 2.2 million miles per hour. It is starving the galaxy.
Death by 1,000 cuts, as the researchers called it.
Right. It's expelling the cold gas needed for star formation. This feedback loop is critical. If these black holes formed early and massive, as you suggest, they would have dominated the thermal history of the universe. They would have shut down star formation before it even really got started in some places.
And that reinforces the top-down view. If the black hole is the cosmic assassin, it dictates the life of the galaxy. In the standard model, the black hole is almost a passive byproduct of the galaxy's evolution, just eating the scraps. But in Pablo's galaxy, and in UHZ1, the black hole is the anchor. It's the tyrant. It decides if the galaxy lives or dies. This supports the idea that the black hole is the primary structure around which the rest of the system organizes, or fails to organize.
I see why you frame it that way. The black hole as the tyrant definitely fits the heavy seed narrative. But feedback exists in the hierarchical model too. In fact, we need feedback to explain why modern galaxies aren't just giant balls of stars. The difference is just timing. You think the tyrant was there from the start. I think the tyrant grew into power. But Pablo's galaxy shows us that by cosmic noon, the black hole has definitely taken charge.
So where does that leave us? We have UHZ1 with its impossible mass ratio, a penguin the size of the iceberg. We have little red dots that turn out to be hidden engines, far denser than galaxies should be. We have the cliff looking like a black hole star, and we have a timeline that is just squeezing the life out of the slow growth model.
I think we are moving toward a synthesis. Look, I am not ready to abandon the standard model entirely, because for the vast majority of the universe's history, it works. Stellar seeds explain the lower mass black holes we see today perfectly well. However, I have to concede that the sheer abundance of these little red dots and the existence of extreme outliers like UHZ1 suggests that the standard model cannot be the only story.
A multimodal timeline.
Precisely. It seems likely that the universe had multiple ways to make a monster. In the earliest, hottest epochs, perhaps direct collapse, or when Zirkene's not quite primordial seeds were dominant, creating the giants like UHZ1. But as the universe cooled and the first stars died, the light seed mechanism took over, aided by those super-Eddington feeding frenzies.
I can agree with a blended view, as long as we admit that the heavy seed wasn't just a curiosity, it was likely the primary architect of the early universe's structure. The universe was more efficient at making monsters than we gave it credit for. It didn't wait for stars to do the heavy lifting.
And the exciting part is, we don't have to guess for much longer. We are working with JWST right now, which is like looking through a soda straw. Incredible depth, but a tiny field of view. We're seeing individual anomalies.
But the cavalry is coming. Euclid is already up, mapping the dark matter scaffolding. And the Nancy Grace Roman telescope, that is the game changer.
Absolutely. Roman will have a field of view 100 to 200 times wider than JWST. It's going to turn these anecdotes into statistics. It will hunt for those featherweight primordial seeds and early quasars across the entire sky.
It will tell us if UAZ-1 is a freak of nature or the norm. And personally, I'm betting on the norm. I think Roman is going to find that the early universe was absolutely crowded with these direct collapse objects.
We shall see. If Roman finds thousands of them, I will happily concede that the hierarchical model is a relic of the past. But until then, I hold that a feeding frenzy is a powerful thing.
It is, but a heavy seed is a head start you just can't beat.
What we can agree on is that the dark ages of the universe were not dark at all. They were gravitationally violent, active, and full of monsters. The crisis of too big, too early has effectively rewritten the first chapter of cosmic history.
And it's a much better story than the one we had before.
On that, we agree. Thank you for joining us on this journey to the edge of time.
It was a pleasure to break the universe with you.
And thank you to our listeners. Welcome to the new history of the cosmos. This has been The Debate.